Good evening, everyone. How is everyone doing? Glad you guys are doing well. I'm also doing well, thanks. So happy winter solace. And this means we are currently tonight will be the longest night and shortest day of the year. So, Ms. Visaki, why do you say a bad debugging session? Pointer arithmetic. I remember when I have done that many years ago. That is horrible. That's one of the horrible parts of C++ and C. Yes, especially arrays. Yes. If I'm correct, somewhere in my first year, was one of our projects, we needed to create a two-dimensional array making use of pointers and arrays in C++ to create a game. I still have it somewhere, but I can't remember exactly what I did. But I have it somewhere. So let's begin with pretty sure I have the code somewhere on an external hard drive. So tonight's lecture, we're going to have a small shift. So last week, we ended off with modern cosmology. So now we've looked from everything to what is a star, how do stars form, what happens in the life cycle of stars. Then we started zooming out a little bit, and what is star clusters. Then we started looking at a Milky Way galaxy and galaxies, how galaxies evolve and form. Then we went over to cosmology and say, what is the Big Bang? How did the Big Bang occur? How does everything fit in together? But now we are zooming in again. And we are going to look at solar systems, planets, and see how planets are formed. And this will build up to the rest of the planets in our solar system. So in this chapter, we are going to look at the Great Chain of Origins, a survey of solar systems, the story of planet building, and planets orbiting other stars, also known as exoplanets. So we are all familiar with this representation, Sun and Mercury all the way to Neptune. I only disagree with this in one sense. For me, Pluto should have been kept a planet, but there was a convention held led by Neil deGrasse Tyson and a few others in the international astronomy community, and they changed the definition of a planet, so Pluto isn't classified as a planet anymore, but rather as a planetoid. For me, Pluto should have been kept a planet purely out of tradition, but the international astronomy community decided now, unfortunately, Pluto is not a planet anymore. So you've studied the appearance, origin, structure, and evolution of stars, galaxies, and the entire universe. So far, though, your studies have left out one important type object, planets. Now it is time for you to fill in that blank. In this chapter, once you learn the evidence of how star system is formed, you can understand how the process you have been studying produced Earth, your home planet. And because thousands of planets have been discovered around other stars, you can be confident that those processes are not unique to our solar system. As you explore our solar system in space and time, you will find answers to four important questions. Firstly, what are the observed properties of the solar system as a whole? Second, how did the solar system form? Thirdly, how do planets form? And then lastly, what do astronomers know about other planetary systems? So this is artist representation. So dust in debris belts around all the main sequence star indicates ongoing collisions of asteroids and comets. Such activity in our solar system is ultimately driven by gravitational influence of planets. Debris belt edges may be defined and adjacent orbits of planets. The inferred architecture of the inner, so top and outer bottom parts of the Epsilon Eridani planetary system are shown in comparison with parts of our own solar system. You can study the solar system for many reasons. You can study Earth and its sibling planets because, as you are about to discover, there are almost certainly more planets in the universe than stars. Above all, you can study the solar system because it is your home in the universe. Because humans are an intelligent species. We have the ability and responsibility to wonder where we are and what we are. Our kind have inhabited the solar system for at least 100,000 years, but only within the last few hundred years have we begun to understand what a solar system is. You are linked through a great chain of origins that leads back through time to the instant when the universe began 13.8 billion years ago. The gradual discovery of the links in that chain has been one of the most exciting adventures of the human intellect. In earlier chapters, you studied some of that story. The origin of the universe and the Big Bang, the formation of galaxies, the origin of stars, and the growth of the chemical elements. Now you will explore further to consider the origins of planets. The universe began in the Big Bang. By the time the universe was a few minutes old, the protons, neurons, and electrons in your body had come into existence. You are made of very old matter. Although those particles formed quickly, they were not linked together to form many of the atoms that are common today. The matter in the early universe was about 75% hydrogen by mass and 25% helium. Although your body does not contain helium, it does contain many of the ancient hydrogen atoms unchanged since the universe began. Evidence indicates that almost no atoms heavier than helium were made in the Big Bang. Within a few 100 million years after the Big Bang, matter began to collect to form galaxies containing billions of stars. You have learned that nuclear reactions inside stars are where low-mass atoms such as hydrogen are combined to make heavier atoms. Generation after generation of stars cook the original particles, fusing them into atoms such as carbon, nitrogen, and oxygen that are common in your body. Even the calcium atoms in your bones were assembled inside stars. Massive stars produce iron in their cores, but much of that iron is destroyed when the core collapses and the star explodes as a supernova. Most of the iron on Earth and in your body was produced instead by carbon fusion in type 1a supernova explosions and by the decay of radioactive atoms in the expanding matter ejected by type 2 supernovae. Atoms heavier than iron, such as gold, silver, and iodine, are created by rapid nuclear reactions that can occur only during supernova explosions. Iodine is critical to the function of your thyroid gland, and you probably have gold and silver jewelry or dental fillings. Realize that these types of atoms, which are part of your life on Earth, were made during the violent deaths of massive stars long ago. Our galaxy contains at least 100 billion stars, of which the Sun is one. Astronomers have a variety of evidence that the Sun formed from a cloud of gas and dust about 5 billion years ago, and the atoms in your body were part of that cloud. The stories of how the cloud gave birth to planets and how the atoms in your body found their way onto Earth and into you make up the story of this chapter. As you explore the origin of the solar system, keep in mind the great chain of origins that created the atoms. As a geologist Preston Cloud remarked, "Stars have died that we might live." Firstly, we're going to look at the solar nebula theory. Over the last 2 centuries, astronomers have proposed 2 kinds of hypotheses for the origin of planets in our solar system. The catastrophic hypothesis proposed that planets formed from some improbable event, such as the collision of the Sun and another star. Evolutionary hypothesis proposed that the planets formed gradually and naturally as the Sun formed. Since around the middle of the 20th century, evidence has become overwhelming for the evolutionary scenario. In fact, the evolutionary hypothesis is so comprehensive and explains so many of the observations that it can be considered to have graduated from just a hypothesis to being a properly called theory. Today, astronomers are continuing to refine the details of that theory. So what is happening in this theory? So the solar nebula theory supposes that planets form in the rotating disks of gas and dust around young stars. So here we'll see a star in the center, so the rotating gas contracts and flattens to become a thin disk of gas and dust around the forming Sun at the center. Planets grow from gas and dust in the disk and are left behind when the disk clears. We have seen clear evidence that disks of gas and dust are common around young stars. Bipolar flows from protostars were the first evidence of such disks, but modern techniques can image the disks directly. The evidence is strong that our own planetary system formed in such a disk-shaped cloud around the Sun. When the Sun became luminous enough, the remaining gas and dust were blown away into space, leaving the planets orbiting the Sun. So, as you saw here, it feels like Darwin's theory almost. You'll see in nature, evolution and nature goes hand to hand. So I can explain the previous slide. So yes, so right here when you have still a young Sun that's being formed, and so really formed and is now in the protostar phase, there will still be a cloud of gas around the Sun. And that gas cloud will contract, and due to these particles colliding and contracting, that will form planets. And once the Sun in the inside is luminous enough, it will blow away the dust, and then what remains is the stars. So the stars doesn't form from the middle of the cloud. So you can think about it as a so what's the best way? So let's get a whiteboard out. So what happens is, in short, this will be the star or Sun in the middle of the cloud. Then around will be our... So right here we will have different particles that's for us everywhere in the cloud. And that's orbiting the Sun. And these particles will collide one another to form bigger particles. And these particles will collide and contract to form even bigger particles. And those particles will collide and contract to form even bigger particles. And that particles that's being created and clumped together and contracted is the planets being formed. I think this will become a little bit more clearer as we progress through the lecture. That we're going to discuss in this lecture as well. There's a few factors, depending if it's a terrestrial planet or a Gideon planet, but we will get to that later in this lecture. So it will become clear in a moment. So many of the young stars in the Orion Nebula are surrounded by disks of gas and dust. But intense light from the brightest star in the neighborhood is evaporating the disks to form expanding clouds of gas. These particular disks may evaporate before they can form planets. But a large number of such disks show that planet construction material around young stars is common. According to the solar nebula theory, Earth and other planets of the solar system formed billions of years ago as the sun condensed from a cloud of interstellar gas and dust. If planet formation is a natural part of star formation, most stars should have planets. To test their hypothesis about how the solar system was born, astronomers searched the present solar system for evidence of its past. In this section, you will survey the solar system and compile a list of its most significant characteristics that are potential clues to how it formed. You can begin with the most general view of the solar system. It is, in fact, almost entirely empty space. Imagine reducing the scale of the solar system until Earth is the size of a grain of salt table, about 0.3 millimeters in diameter. The moon is a speck of paper of about 1 centimeter away, and the sun is the size of a small plum located 4 meters from Earth. Jupiter is the size of an apple seed and it's 21 meters from the sun. Neptune, at the edge of the planetary zone, is the large grain of sand more than 120 meters from the central plum. Your model solar system would be larger than 2 football fields, and would need a powerful microscope to detect the asteroids orbiting between Mars and Jupiter. The planets are tiny specks of matter scattered around the sun, the last remains of the solar nebula. The planets revolve around the sun in orbits that lie close to a common plane. The orbit of Mercury, the closest planet to the sun, is tipped 7 degrees to Earth's orbit. The rest of the planet's orbital planes are inclined by no more than 3.4 degrees. As you can see, the solar system is basically flat and disc-shaped. The rotation of the sun and planets on their axis also seem related to the rotation of the disk. The sun rotates with its equator inclined only 7.2 degrees to Earth's orbit. And most of the other planets' equators are tipped less than 30 degrees. The rotation of Venus and Uranus are peculiar, however. Venus rotates backward compared with the other planets, whereas Uranus rotates on its side with its equator almost perpendicular to its orbit. You will explore these planets in detail in chapter 17 and 18, but later in this chapter you will be able to understand how they might have acquired their peculiar rotations. There is a preferred direction of motion in the solar system, counterclockwise, as seen from the north. All the planets revolve around the sun in that direction, with the exception of Venus and Uranus. All the planets also rotate on their axis in that direction. Furthermore, nearly all the moons in the solar system, including Earth's moon, orbit around the respective planets in that same direction. with only a few exceptions. Revolution and rotation in the solar system follow a single theme. Apparently, these motions today are related to the original rotation of the disk of solar system construction material. And now we can classify two kinds of planets. Perhaps the most striking clue to the origin of the solar system comes from the obvious division of the planets into two groups: the small Earth-like worlds and the giant Jupiter-like worlds. The difference is so dramatic that you are led to say, this must mean something. So notice three important points and learn two new terms this is a good question for the exam. The two kinds of planets are distinguished by the location. The four inner terrestrial planets are different from the four Jovian planets. So remember, hint for the test and exam: terrestrial planets, Jovian planets. Craters are common. Almost every solid surface in a solar system is covered with craters. And lastly, two groups of planets are also distinguished by properties such as number of moons and presence or absence of rings. The theory of the origin of the planets needs to explain these properties. So Jovian comes from the word Jupiter, so it means all the gas planets. So the Jovian planets are Jupiter, Saturn, Uranus, Neptune. The division of planets into two groups are clue to how our solar system formed. The present properties of individual planets, however, don't tell everything you need to know about their origins. The planets have evolved since they formed. For further clues about the origin of planets, you can look at smaller objects that have remained largely unchanged since soon after the birth of the solar system. So what does the term gas planet mean, sir? So Earth and Mars are a good example. We have a solid surface, so we call that terrestrial planets. But Jupiter doesn't have a solid surface. Saturn doesn't have a solid surface. Instead, they have different layers of gas with different densities that construct the planet. No, gas planets are not craters. You can only get craters on a terrestrial world. So firstly, we're going to look at cosmic debris. The sun and planets are not the only products of the solar nebula. The solar system is littered with several kinds of space debris, such as asteroids, comets, and meteorites. Those objects will be considered in further detail in Chapter 19, but they are mentioned here because they are a rich source of information about the origin of the planets. The asteroids, sometimes called minor planets, are small rocky worlds, most of which orbit the Sun in a belt between the orbits of Mars and Jupiter. More than 100,000 asteroids have orbits that are charted. It is a common misconception that asteroids are the remains of a planet that broke apart. In fact, planets are held together very tightly by their gravity and do not break apart. Astronomers recognize the asteroids as debris left over from the failure of a planet to form at a distance of about 3 AU from the Sun. So what happens if an asteroid goes into gas planet? Will it go in till it matches the density and stay there? So usually what will happen is, as we will learn in tomorrow's lecture, the deeper you go into these gas planets, the higher the pressure. So most likely the asteroid will be crushed by the pressure of the gas giants. Spectroscopic observations indicate that asteroid surfaces are made up of a variety of rocky and metallic materials. Note that metal is used here in a familiar sense, referring to substances such as iron rather than stellar astronomer sense, meaning any element other than hydrogen and helium. Photographs returned by robotic spacecraft show that asteroids are generally irregular in shape and covered with craters. Those observations will be discussed in detail in Chapter 19, but in this quick survey of the solar system, you have enough information to conclude that the solar nebula included elements that compose of rocks and metal, and also that collisions have played an important role in the solar system's history. So here is a good example of an asteroid. So over a period of 3 weeks, the NEAR spacecraft approached the asteroid Eros and recorded a series of images arranged here in an interesting pattern, showing the asteroid's irregular shape and 5-hour rotation period. Eros is 34 kilometers long. This close-up of the surface of Eros showed an area of about 11 kilometers from the top to the bottom. Yes. So depending on which layer of the atmosphere we are in, we have a different density and different pressure. And yes, that's exactly what happened with Cassini. Thank you, Mr. Groenewald. Since 1992, astronomers have discovered more than 1,000 small dark icy bodies orbiting in the outer fringes of the solar system beyond Neptune. This collection of objects is called the Kuiper Belt, after astronomer Gerard Kuiper, who predicted their existence in the 1950s. There are probably 100 million objects larger than 1 kilometer in the Kuiper Belt, many more than in the asteroid belt. A successful story for the formation of the solar system should also explain how the Kuiper Belt objects, or in short KBOs, came to be where they are. You will find out more about the origin of the Kuiper Belt in Chapter 18. Asteroids move in defined patterns because everything is locked in a certain orbits, and orbits are very important. So usually when an asteroid breaks through from the asteroid belt, then it's usually trouble, because then there can be a collision course to Earth, one of the other planets, but usually they're on stable orbits. So in this image, we can see the 4 terrestrial worlds, the asteroid belt. Here we can see the 4 Jovian worlds, and here is Pluto, and here is the Kuiper Belt. Putting this in another way around, here we can see the Kuiper Belt past Neptune around our own sun. In contrast to the rocky asteroids and dark Kuiper Belt objects, the brightest comets can be seen with the naked eye and are impressively beautiful objects. A comet may be visible for many weeks as it sweeps through the inner solar system. Most comets are faint, however, and difficult to locate at even the brightest. The nuclei of comets are ice-rich bodies a few kilometers or tens of kilometers in diameter, similar in size to asteroids. Like asteroids, comets are understood to be left over from the origin of the planets and provide evidence that at least some parts of the solar nebula had abundant icy material. You will discover more about the composition and history of comets in Chapter 19. A comet nucleus remains frozen and inactive while it is far from the Sun. If the comet's orbit carries it into the inner solar system, the Sun's heat begins to vaporize the ices, releasing gas and dust. The flow of solar wind plus radiation pressure exerted by sunlight pushes the gas and dust away, forming a long tail. As a result, the tail of a comet always points approximately away from the Sun, no matter what direction the comet itself is moving. The beautiful tail of a comet can be longer than an AU, although it's produced by a relatively tiny nucleus only a few kilometers in diameter. So here we can see a comet coming into the solar system. As it approaches the sun, its ice core starts to evaporate and the gases are released, and we see this beautiful tail being pushed by solar wind and cosmic radiation from the sun. And here is a nice image of a comet. Unlike the stately comets, meteors flash across the sky in momentary streaks of light. They are commonly called shooting stars. Of course, they are not stars, but small bits of rock and metal colliding with Earth's atmosphere. Sorry about that. They're commonly called shooting stars. Of course, they are not stars, but small bits of rock and metal colliding with Earth's atmosphere and bursting into incandescent vapor because of friction with the air about 80 kilometers above the ground. This vapor condenses to form dust that settles slowly to Earth, adding about 40,000 tons per year to the planet's mass. So yes, I have seen a comet, and I've also seen a few meteors as well. A meteor is a sudden streak of glowing gases produced by a bit of material falling into Earth's atmosphere. Friction with the air vaporized the material about 80 kilometers above Earth's surface. This meteor is seen against the background part of the Milky Way. So over here. Technically, the word meteor refers to the streak of light in the sky. In space, before its fiery plunge, the object is called a meteorite. And many part of it that survives the fiery passage to Earth surface is called a meteorite, meteoroid, and then a meteorite. Most meteoroids are specks of dust, grains of sand, or tiny pebbles. Almost all the meteors you see in the sky are produced by meteoroids that weigh less than 1 gram. Only rarely a meteoroid massive enough and strong enough to survive its plunge and reach Earth's surface survive. Thousands of meteorites have been found, and you will learn more about the various types in Chapter 19. Meteorites are mentioned here for one specific clue. They can give you concerning the solar nebula. Meteorites can reveal the age of the solar system. And how do we determine the age of the solar system? According to the solar nebula theory, the planet should be about the same age as the Sun. The most accurate way to find the age of a rocky body is to bring a sample into the laboratory and analyze the radioactive elements it contains. When a rock solidifies, it incorporates known percentages of that chemical elements. A few of these elements have forms called isotopes that are radioactive, meaning they gradually decay into other isotopes. For example, potassium-40, called a parent isotope, decays into calcium-40 and argon-14, called daughter isotopes. The half-life of a radioactive substance is the time it takes for half of the parent isotope atoms to decay into daughter isotope atoms. The abundance of radioactive substance gradually decreases as it decays, and the abundances of daughter substances gradually increase. The half-life of potassium-40 is 1.3 billion years. If you also have information about the abundances of the elements in the original rock, you can compare those with the present abundances and find the age of the rock. For example, if you study a rock and find that only 50% of the potassium-40 remains, and the rest has become a mixture of daughter isotopes, you conclude that one half-life must have passed and the rock is 1.3 billion years old. In image A, we can see the radioactive parent, so atoms in red, in a mineral sample decay into daughter atoms blue. Half of the radioactive atoms are left after one half-life, a fourth of the two half-lives, an eighth of the three half-lives, and so on. Then image B. Radioactive dating shows that this fragment of the Allen meteorite is 4.56 billion years old. It contains a few even older interstellar grains, which formed long before our solar system did. Potassium isn't the only radioactive element used in radioactive dating. Uranium-238 decays with a half-life of 4.5 billion years to form lead-206 and other isotopes. Rubidium-87 decays into strontium-87 with a half-life of 47 billion years. Any of these substances can be used as a radioactive clock to find the age of mineral samples. Of course, to find a radioactive age, you need to get a sample into the laboratory, and the only celestial bodies of which scientists have samples are Earth, the Moon, Mars, and meteorites. The oldest Earth rocks so far discovered and dated are tiny zircon crystals from Australia that are 4.4 billion years old. That does not mean that Earth formed 4.4 billion years ago. As you will see in the next chapter, the surface of Earth is active, and the crust is continuously destroyed and reformed with material welling up from beneath the crust. Although no one has yet been to Mars, over a dozen meteorites found on Earth have been identified by the chemical compositions as having come from Mars. Most of these have ages of only a billion years or so, but one has an age of approximately 4.5 billion years. Mars must be at least that old. The most important source for determining the age of the solar system is meteorites. Radioactive dating of meteorites yields a range of ages, but there is a fairly precise upper limit. Many meteorite samples have ages of 4.56 billion years old, and none are older. That figure is widely accepted as the age of the solar system and is often rounded to 4.6 billion years. The true ages of Earth, the Moon, and Mars are also assumed to be 4.6 billion years, although no rocks from those bodies have yet been found that have remained unaltered for that entire stretch of time. One last celestial body deserves mention: the Sun. Astronomers estimate the age of the Sun to be about 5 billion years. But that is not radioactive date because we have no samples of radioactive material from the Sun. Instead, an independent estimate for the age of the Sun can be made using helioseismological observations and mathematical models of the Sun's interior. This yields a value of about 5 billion years, plus or minus 1.5 billion years, a number that is in agreement with the age of the solar system, derived from the age of meteorites. Apparently, all the bodies in the solar system formed at about the same time, some 4.6 billion years ago. You can add this as the final item to your list of characteristic properties of the solar system. The challenge for modern planetary scientists is to compare the characteristics of the solar system with predictions of the solar nebula theory so they can work out details of how the planets are formed. Everything astronomers know about a solar system and star formation suggests that a solar nebula was a fragment of an interstellar gas cloud. Such a cloud would have been mostly hydrogen with some helium and small amounts of heavier elements. That is precisely what you see in the composition of the Sun. Analysis of the solar spectrum shows that the Sun is mostly hydrogen, with a quarter of its mass being helium and only about 2% being heavier elements. Of course, nuclear reactions have fused some hydrogen to helium, but this happens in the Sun's core and has not affected the composition of its surface and atmosphere, which are the parts you can observe directly. That means the composition revealed in the Sun's spectrum is essentially the composition of the gases from which the Sun formed. This must have been the composition of the solar nebula, and you can also see that composition reflected in the chemical compositions of the planets. The inner planets are composed of rock and metal, and outer planets are rich in low-density gases such as hydrogen and helium. The chemical composition of Jupiter resembles the composition of the Sun, but if you allowed low-density gases to escape from a blob of stuff with the same overall composition as the Sun or Jupiter, the relative proportions of the remaining heavier elements would resemble the chemical composition of Earth and other terrestrial planets. An important clue to understanding the process that converted the nebula gas into solid matter is the variation in density among solar system objects. You have already noted that the four inner planets are small and have high densities, resembling Earth, whereas the outermost planets are large and have low density, resembling Jupiter. Even among the four terrestrial planets, you will find a pattern of slight differences in density. Merely listing the above observed densities of terrestrial planets does not reveal the pattern clearly because Earth and Venus, being more massive, have stronger gravity and have squeezed their interiors to higher densities. The uncompressed densities, the densities the planets would have if their gravity did not compress them, or to put it another way, the average densities of the original construction material, can be calculated using the actual densities and masses of each planet. In general, the closer a planet is to the Sun, the higher its uncompressed density. So here we can see the observed density and compressed density of the four innermost planets. According to the solar nebula theory, the observed pattern of planet densities originated when solid grains first formed, a process called condensation. Solid particles condensed from the gas of the nebula as it cooled. The kind of matter that could condense in a particular region depended on the temperature of the gas there. In the inner regions close to the Sun, the temperature was evidently 1500 Kelvin or so. The only materials that can form grains at that temperature are compounds with high melting points, such as metal oxides and pure metals, which are very dense. Further out in the nebula, it was cooler, and silicates, so rocky material, could also condense. In addition to metal, these are less dense than metal oxides and metals. Mercury, Venus, Earth, and Mars are evidently composed of a mixture of metals, metal oxides, and silicates, with proportionality more metals close to the Sun and more silicates further from the Sun. Yes, that density is due to gravity. You are correct, Mr. Visagie. Even further from the Sun, there was a boundary called the ice line, beyond which vapor could freeze to form ice particles. Yet, a little further from the Sun, compounds such as methane and ammonia could condense to form other types of ice. Water vapor, methane, and ammonia were abundant in the solar nebula. So beyond the ice line, the nebula would have been filled with a blizzard of ice particles, mixed with some small amounts of silicate and metal particles that could also condense there. Those ices are low-density materials. The densities of Jupiter and the outer planets correspond to a mix of ices plus relatively small amounts of silicates and metal. The sequence in which a different material condenses from the gas as you move away from the Sun toward a lower temperature is called the condensation sequence. It suggests that the planets forming at different distances from the Sun should have accumulated from different kinds of materials in a predictable way. Yes, we're going to have a 5-minute break again. People who have read a little bit about the origin of the solar system may hold the common misconception that the matter in a solar nebula was sorted by density, with the heavy rock and metal sinking toward the Sun and the low density gases being blown outward. That is not the case. The chemical composition of the solar nebula was originally roughly the same throughout the disk. The important factor was temperature. The inner nebula was hot and only metals and rock could condense there, whereas the cold outer nebula could form lots of ices along with metal and rock. The ice line seems to have between Mars and Jupiter, and it separates the region for formation of the high density terrestrial planets from that of the low density Jovian planets. In the development of the planets from the material of the solar nebula disk, 3 processes operated to collect solid bits of matter, metal, rock, and ice, into larger bodies called planetesimals, which eventually made planets. The study of planet building is the study of the 3 processes. In a previous section, you learned a little about the process of condensation. Planetary development in the solar nebula began with the formation of dust grains by condensation. A particle grows by condensation when it adds matter, 1 atom of molecule at a time, from surrounding gas. Snowflakes, for example, grow by condensation in Earth's atmosphere. In a solar nebula, dust grains would have been bombarded continuously by atoms of gas, and some of those stuck to the grains. A microscopic grain capturing a layer of gas molecules on its surface increases its mass by a much larger fraction than a gigantic boulder capturing a single layer of molecules. For that reason, condensation can increase the mass of a small grain rapidly, but as the grain grows larger, condensation becomes less effective and other processes became more important. Sorry for the typos in the slides. It looks like I was tired when I created these slides. So sorry about that. I will fix that as well. The second process of planetesimal formation is accretion, and we've already learned a lot about accretion disks. The sticking together of solid particles. You may have seen accretion in action if you have walked through a snowstorm with big fluffy flakes. If you caught one of those flakes on your glove and looked closely, you saw that it was actually made up of many tiny individual flakes that had collided as they fell and accreted to form larger particles. In a solar nebula, the dust grains were on average no more than a few centimeters apart, so they collided frequently and could accrete into larger particles. When the particles grew to sizes larger than a centimeter, they would have been subjected to a new process that tended to concentrate them. One important effect was that the growing solid objects would have collected into the plane of the solar nebula. Small dust grains could not fall into the plane because of the turbulent motions of the gas kept them stirred up, but larger objects had more mass, and gas motions could not have prevented them from settling into the plane of the spinning nebula. Astronomers calculate this would have concentrated the larger solid particles into a relatively thin layer about 0.01 AU thick that would have made further growth more rapid. There is no clear distinction between a very large grain and very small planetesimal, but you might consider an object to be a planetesimal when its diameter approaches a kilometer. What do the planetesimals look like? You get a clue from this photo of the 5 kilometer wide nucleus of a comet, and the comet's name is WAL2. Whether rocky or icy, planetesimals must have been small, irregular bodies scattered by craters from collisions with other planetesimals. This concentration of large particles and planetesimals into the plane of the nebula has some resemblance to the flattening of a forming galaxy. And a process also found in galaxies may have become important once the plane of planetesimals formed. Computer models showed that a rotating disk of particles should have been gravitationally unstable and would have been disturbed by a spiral density wave resembling the much larger ones found in spiral galaxies. Those waves could have further concentrated the planetesimals and helped them coalesce into objects of about 100 kilometers in diameter. Through these processes, according to the solar nebula theory, the disk of gas and dust around the forming sun became filled with trillions of solid particles ranging in size from pebbles to tiny planets. As the largest began to exceed 100 km in diameter, the third process began to affect them, and a new stage of planet building began, the formation of protoplanets. The coalescing of planetesimals eventually formed protoplanets, the name for massive objects destined to become planets. As these larger bodies grew, a new process helped them grow faster and altered their physical structure. If planetesimals had collided at orbital velocities, they would have been unable to stick together. A typical orbital velocity in a solar system is about 10 kilometers per second. Head-on collisions at this velocity would vaporize the material. However, the planetesimals were all moving in the same direction in a nebular plane and didn't collide head-on. Instead, they merely rubbed shoulders, to speak, at low relative velocities. Such gentle collisions would have been more likely to combine planetesimals than to shatter them. The largest planetesimals would grow the fastest because they had the strongest gravitational field. Their stronger gravity could affect additional material. The gravity could also hold on to a cushioning layer of soil that would trap fragments. Astronomers calculate that the largest planetesimals would have grown quickly to protoplanetary dimensions, sweeping up more and more material. Protoplanets had to begin growing by accumulating solid material because they did not have enough gravity to capture and hold large amounts of gas. In a warm solar nebula, the atoms and molecules of gas were traveling at velocities much larger than the escape velocities of the modest-sized protoplanets. Therefore, in their early development, the protoplanets could grow only by attracting solid bits of rock, metal, and ice. Once a protoplanet approached a size of 15 Earth masses or so, however, it could begin to grow by gravitational collapse, the rapid accumulation of large amounts of infalling gas from the nebula. The theory of protoplanet growth into planets supposes that all the planetesimals had about the same chemical composition. The planetesimals accumulated to form a planet-sized ball of material with homogeneous composition throughout. Once the planet formed, heat would begin to accumulate in its interior from the decay of short-lived radioactive elements. The violent impact of infalling particles would also have released energy called heat of formation. These two heating sources would eventually have melted the planet and allowed it to differentiate. Differentiation is the separation of material according to density. Remember this definition for the exam. Once a planet melted, the heavy metals such as iron and nickel, plus elements chemically attracted to them, would settle to the core, while the lighter silicates and related materials floated to the surface to form a low-density crust. The scenario of planetesimals combining into planets that subsequently differentiate is shown in the following figure. So here we can see planetesimals contain both rock and metal. A planet grows from the uniform planetesimals. The resulting planet is homogeneous in composition. Heat from the radioactive decay and planetesimal infall causes differentiation. The resulting planet has a metal core and a low-density crust. The process of differentiation depends partly on the presence of short-lived radioactive elements whose rapid decay would have released enough heat to melt the interior of planets. Astronomers known such radioactive elements were present because very old rock from meteorites contained daughter isotopes such as magnesium-26. The isotopes is produced by the decay of aluminium-26 with a half-life of only 0.74 million years. The aluminium-26 and similar short-lived radioactive isotopes are gone now, but they must have been produced in a supernova explosion that occurred shortly before the formation of the solar nebula. In fact, some astronomers suspect that a supernova explosion could have triggered the formation of the Sun and other stars by compressing interstellar clouds. Thus, our solar system may exist because of a supernova explosion that occurred about 4.6 billion years ago. If planets formed by accretion of planetesimals and were later melted by radioactive decay and the heat of formation, then Earth's early atmosphere may have consisted of a combination of gases delivered by planetesimal impacts and released from a planet's interior during differentiation. The creation of a planetary atmosphere from a planet's interior is called outgassing. Given the location of Earth in the solar nebula, planetary scientists calculate that the gases released from its interior during differentiation would not have included much water as Earth has now. So astronomers hypothesized that some of the Earth's water and atmosphere accumulated late in the formation of the planet. As Earth swept up volatile-rich planetesimals, these icy planetesimals would have formed in the cool outer parts of the solar nebula and could have been scattered toward terrestrial planets by encounters with the Jovian planets, creating a comet bombardment. According to the solar nebula theory, the Jovian planets could begin growing by the same process that built the terrestrial planets. However, in an inner solar nebula, only metals and silicates could form solids, so the terrestrial planets grew slowly. In contrast, the outer solar nebula contained not just solid bits of metals and silicates, but also ices that included plentiful hydrogen. Astronomers calculate that the Jovian planets would have grown faster than the terrestrial planets and quickly became massive enough to begin even faster growth by gravitational collapse, drawing in large amount of gas from the solar nebula. The terrestrial planet zone did not include ice particles, so those planets developed relatively slowly and never became massive enough to grow further by gravitational collapse. The Jovian planets must have reached the present size no more than about 10 million years, before the Sun became hot and luminous enough to blow away the remaining gas in the solar nebula, removing the raw material for further Jovian growth. As we will learn in the next section, disturbances from outside the forming solar system may have reduced the time available for Jovian planet formation even more severely. The terrestrial planets, in comparison, grew from solids and not from gas, so they could have continued to grow by accretion from solid debris and left behind after the gas was removed. Mathematical models indicate that terrestrial planets were at least half finished within 10 million years, but could have continued to grow for another 20 million years or so. The solar nebula theory has been very successful in explaining the formation of the solar system, but there are some problems, and the Jovian planets are the troublemakers. So let's take a 5-minute break. So I will see you all back at 6:35. Okay, it's 6:35, so let's continue with this lecture. So now we're going to look at the four troublemakers. New information about star formation process makes it hard to explain the formation of the Jovian planets. And this has caused astronomers to expand and revise the theory of planet formation. The new information is that gas and dust disks around newborn stars don't last long. You have seen images of dusty gas disks around young stars in the Orion star-forming region. Those disks are being evaporated by intense ultraviolet radiation from O and B stars forming nearby. Astronomers have calculated that nearly all stars form in clusters containing O and B stars, so this evaporation may happen to most disks. Even if a disk does not evaporate quickly, the gravitational influence of the crowded stars in a cluster could strip away the outer parts of the disk. Those are troublesome observations because they seem to indicate that disks can't last longer than about 10 million years and may evaporate within the astronomically very short span of 100,000 years or so. That's not long enough to grow Jovian planet by the combination of condensation, accretion, and gravitational collapse proposed by the standard solar nebula theory. Yet Jovian planets are common. In the final section of this chapter, you will see evidence that astronomers have found planets orbiting other stars, and almost all of the planets discovered so far have the mass of Jovian planets. There may also be many terrestrial planets orbiting those stars that are too small to be detected at present. But the important point is that there are lots of Jovian planets around. How they form quickly enough before the disks of raw material evaporate is referred to as the Jovian problem. Mathematical models of solar nebula have been produced using specially built computers running programs that take weeks to finish a calculation. The results showed that the rotating gas and dust of the solar nebula could have become unstable and formed Jovian planets by skipping straight to the step of gravitational collapse. That is, massive planets may have been able to form by direct collapse of gas without first forming a dense core by condensation and accretion of solid material. Jupiter and Saturn can form in these direct collapse models in only a few thousand years. If the Jovian planets formed in this way, they could have formed before the solar nebula disappeared, even if the nebula was eroded quickly by neighboring massive hot stars. The original nebula theory hypothesized that the planets formed by accreting a core, and then, if they became massive enough, accelerated growth by gravitational collapse. The proposed modification to the theory suggests that the outer planets could have skipped the core accretion phase. Now you have learned enough to put all the pieces of the puzzle together and explain the distinguishable characteristics of the solar system. The disk shape of the solar system is inherited from the motion of material in the solar nebula. The sun and planets and motions mostly revolve and rotate in the same direction because they formed from the same rotating gas cloud. The orbits of the planets lie in the same plane because the rotating solar nebula collapsed into a disk, and the planets formed in that disk. The solar nebula hypothesis is evolutionary in that it calls on continuing processes to gradually build the planets. To explain the odd rotations of Venus and Uranus, however, you may need to consider catastrophic events. Uranus rotates on its side. That might have been caused by an off-center collision with a massive planetesimal when a planet was newly formed, or by gravitational increases with Saturn and Jupiter. Two hypotheses have been proposed to explain the backward rotation of Venus. Theoretical models suggest that a sun produced tides in a thick atmosphere of Venus that could have eventually reversed the planet's rotation, an evolutionary hypothesis. It is also possible that the rotation of Venus was altered by an off-center impact late in a planet's formation, and that is a catastrophic hypothesis. Both may be true. The second item in Table 15.1, the division of the planets into terrestrial and Jovian worlds, can be understood through the condensation sequence. The terrestrial planets formed in the inner part of the solar nebula, where the temperature was high and only substances such as silicates and metals could condense to form solid particles. That produced the small, dense terrestrial planets. In contrast, the Jovian planets formed in the outer solar nebula, where the lower temperature allowed the gas to form large amounts of ices. That allowed the Jovian planets to grow rapidly and become massive, low-density worlds. Also, Jupiter and Saturn are so massive they were able to grow by drawing in cool gas by gravitational collapse from the solar nebula. The terrestrial planets could not do this because they never became massive enough. The heat of formation, so that is the energy released by infawning matter, was tremendous for these massive planets. Jupiter must have grown hot enough to glow with a luminosity of about 1% that of the present Sun. Although it never got hot enough to generate nuclear energy as a star would. Nevertheless, Jupiter is still hot inside. In fact, both Jupiter and Saturn radiate more heat when they absorb from the Sun, so they are evidently still cooling. A glance at a solar system suggests that I should expect to find a planet between Mars and Jupiter at the present location of the asteroid belt. Mathematical models indicate that the reason asteroids are there rather than a planet is that Jupiter grew into such a massive body that it was able to gravitationally disturb the motion of nearby planetesimals. The bodies that could have formed a planet just inward from Jupiter's orbit instead collided at high speeds and shattered rather than combining, were thrown into the Sun or were ejected from the solar system. The asteroids seen today are the last remains of those rocky planetesimals. So in the figure in the textbook CO15 at the beginning of the chapter shows a planetary system observed around another star that also has an asteroid belt just inward of Jovian mass planets. Perhaps that asteroid belt was produced in the same way as ours. The comets, in contrast, are evidently the last of the icy planetesimals. Some have formed in the outer solar nebula beyond Neptune, but many probably formed among the Jovian planets where ices could condense easily. Mathematical models showed that the massive Jovian planets could have ejected some of these icy planetesimals into the far outer solar system. In a later chapter, you will see evidence that some comets are icy bodies coming from those distant locations, falling back into the solar system. The icy Kuiper belt objects appear to be ancient planetesimals that formed in the outer solar system, but were never incorporated into a planet. They orbit slowly far from the light and warmth of the Sun and, except for occasional collisions, have not changed much since the solar system was young. The gravitational influence of the planets deflects some Kuiper belt objects into the inner solar system, where they are also seen as comets. The large satellite systems of Jovian worlds may contain two kinds of moons. Some moons may have formed in an orbit around forming planets in a miniature version of the solar nebula. Some of the smaller moons, in contrast, may be captured planetesimals, asteroids, and comets. The large masses of the Jovian planets would have made it easier for them to capture satellites. In Table 51, you note that all four Jovian worlds have ring systems. And you can understand this by considering the large mass of these worlds and their remote location in the solar system. The large mass makes it easier for a planet to hold onto orbiting ring particles. And being farther from the Sun, the ring particles are not as quickly swept away by radiation pressure and the solar wind. It is hardly surprising then that the terrestrial planets, low mass worlds located near the Sun, have no planetary rings. The last entry in table 15.1 is the common ages of the solar system bodies, and the solar nebula theory has no difficulty explaining that characteristic. According to the theory, the planets formed at the same time as the Sun and should have roughly the same age. The Sun probably formed along with many other stars in a cloud of interstellar material. You have already learned that observations of young stars suggest that radiation and gravitational effects from nearby stars would have tended to disturb and remove the disk of planet construction material around the Sun. Even without those external factors, 4 internal processes would have gradually destroyed the solar nebula. The most important of these internal processes was radiation pressure. When the Sun became a luminous object, light streaming from its photosphere pushed against the particles of the solar nebula. Large bits of matter like planetesimals and planets were not affected, but low mass specks of dust and individual atoms and molecules were pushed outward and evidently driven from the solar system. In a second effect that happened clear the nebula was the solar wind. The flow of ionized hydrogen and other atoms away from the Sun's upper atmosphere. This flow is a steady breeze that rushes past Earth at about 400 kilometers per second. Young stars have even stronger winds than stars of the Sun's age and also irregular fluctuations in luminosity, like those observed in young stars such as T Tauri stars, which can accelerate the wind. The strong surging wind from a young sun may have helped push dust and gas out of the nebula. The third effect that helped clear the nebula was the sweeping up of space debris by planets. All of the old solid surfaces in a solar system are heavily cratered by meteorite impacts. Earth's moon, Mercury, Venus, Mars, and most of the moons in the solar system are covered with craters. A few of these craters have been formed recently by the steady rain of meteorites that falls on all the planets in the solar system. But most of the craters appear to have been formed before roughly 4 billion years ago in what is called the heavy bombardment, as the last of the debris in the solar nebula was swept up by the planets. So here we can see craters that's formed. So every solid surface in the solar system is scarred by craters. Earth Moon has craters ranging from basins, hundreds of kilometers diameter, down to microscopic pits. The surface of Mercury in image B, as photographed by passing spacecraft, shows vast numbers of overlapping craters. The fourth effect was the ejection of material from the solar system by close encounters with planets. If a small object such as a planetesimal passes close to a planet, the small object's path will be affected by the planet's gravitational field. In some cases, the small object can gain energy from the planet's motion and be thrown out of the solar system. Ejection is most probable in encounters with massive planets. So the Jovian planets were probably very efficient at ejecting the icy planetesimals that formed in the region of the nebula. Attacked by the radiation and gravity of nearby stars and racked by internal processes, the solar nebula could not survive very long. Once the gas and dust were gone and most of the planetesimals were swept up, the planets could no longer gain significant mass, and the era of planet building ended. Are there other planetary systems? The evidence says yes. Do they contain planets like Earth? The first such objects have now been discovered. Do you all recognize this telescope? So So this is one of the telescopes we haven't learned yet. It's not WMAP. So are you guys familiar with the Kepler Space Telescope and the Kepler mission? So the Kepler Space Telescope and the Kepler mission was designed to find other planets orbiting other stars. So it's a planet finding mission. So what Kepler did is Kepler looked for other planets around stars that's in the habitable zone. I prefer to refer to the habitable zone as the Goldilocks zone because it's not too cold, not too hot, just fine. So it could be in that zone that it could be life, planets supporting other life. So for Earth, our planetary zone is from Venus all the way up to Mars. So a system we have is Kepler 22. And in Kepler 22, we found the planet named Kepler 22b that's in the habitable zone and could support life. So here is another example of Kepler 62. So Kepler 62, 62f, 62e, 62d, 62c, and 62b, that's all in the habitable zone of that system. Though visible and radio wavelength observations detect dense disks of gas and dust orbiting young stars. For example, at least 50% of the stars in the Orion Nebula are surrounded by such disks. A young star is detectable at the center of most disks, and astronomers can measure that the disks contain many Earth masses of material in a region a few times larger in diameter than our solar system. The Orion star-forming region is only a few million years old, so planets may not have formed inside these disks yet. Furthermore, the intense radiation from nearby hot stars is evaporating the disk so quickly that planets may never have a chance to grow large. The important point for you to consider is that so many young stars have disks. Evidently, disks of gas and dust are a common feature around stars that are forming. So a few comments, Ms. Visalgi, would be interested in knowing that there's a planet with life that is also observing astronomy. Yes, that is a discussion for the last chapter we're going to do for this module. So talking about it, so you guys, going back one slide, do you guys know how Kepler detects these other planets around stars? Yes, so it's when the star dims. So what Kepler does is it looks at a star and it looks at the total flux coming from stars, so the total light coming from that star. And then it waits for a planet to move in front of the star. So if a planet moves in front of the star, it's like a little lunar eclipse, and the total light intensity from that star dips a little bit, and that means there's a planet around that star. Then we take photographs of the star, and then we see how much light dips. From there, we can determine how big the planet is and how far it is away from the star. And then we know what the orbits of those planets is and determine if they are in the Goldilocks zone or not. Yes, the Fermi paradox we're going to discuss in the last chapter of this module. The Hubble Space Telescope also can detect dense disks around young stars in another way. Some disks show up in silhouettes against the nebula that surround the newborn stars. These disks are related to the formation of bipolar flows in that they focus the gas flowing away from a young star into two jets shooting in opposite directions. So here we can see dark bands indicated by arrows are etched on disks of gas and dust around young stars in the Hubble Space Telescope near-infrared images. Planets may eventually form in these disks. These systems are so young that material is still falling inward and being illuminated by light from the stars. In addition to these dense hard disks forming planets around young stars, infrared astronomers have found cold, low-density dust disks around stars much older than the newborn stars in Orion, old enough to have finished forming. These tenuous dust disks are sometimes called debris disks because they are evidently made of dusty debris produced in collisions among smaller bodies orbiting those stars that resemble asteroids. Comets and Kuiper Belt objects in our solar system, rather than dust left over from a regional protostellar disk. That conclusion is based on calculations showing that the observed dust would be removed by radiation pressure in much shorter time than the ages of those stars, meaning the dust there now must have been created relatively recently. Our own solar system contains such second-generation dust produced by asteroid, comets, and Kuiper Belt objects. Astronomers consider the solar system's Kuiper Belt extending beyond the orbit of Neptune as an example of an old debris disk. In some examples of debris disks are around the stars Beta Pictoris and Epsilon Eridani. The disks around Beta Pictoris, an A-type star, more massive and luminous than the Sun, is about 20 times the diameter of our solar system. The dust disk around Epsilon Eridani, which is a K-type star, somewhat smaller than the Sun, is similar to the size of the solar system's Kuiper Belt. Like most of the other known low-density disks, both of these examples have central zones with even lower density. Those inner regions are understood to be places where planets have finished forming and have swept up most of the construction material. In fact, both Beta Pictoris and Epsilon Eridani are now known to have planets. In image A, we can see the dust disks have been detected orbiting a number of stars. But in the visible part of the spectrum, the dust factors of 10 to the 2 to 10 to the 3 times fainter than the stars, which must be hidden behind the masks to make the dust detectable. The second faint inclined disk in the Beta Pictoris system shows the orbital plane of a massive planet. In image B, at a far infrared wavelengths, the dust and debris disk is generally much brighter than a central star. Warps and clumps in these disks can indicate a gravitational influence of planets. So note that this is the same system portrayed as in the opening image of the chapter. Infrared observations reveal that famous star Vega, easily visible in the northern hemisphere summer sky, also has a debris disk. And detailed studies show that most of the dust particles in that disk are tiny. Radiation pressure from Vega should blow away small dust particles quickly. So astronomers conclude that the dust being observed now must have been produced by a big event like the collision of two large planetesimals within the last million years. Fragments from that collision are still smashing into each other and now and then and producing more dust, continuing to enhance the debris disk. This effect has also been found in disks around other mature stars. Such smash-ups probably happen rarely in dust disks, but when they happen, they make the disk very easy to detect. Here we can see such collisions between asteroids that are rare events, but they generate lots of dust in huge numbers of fragments. Notice the difference between the two kinds of planet-related disks that astronomers have found. The low-density dust disks, such as the ones around Beta Pictoris and Epsilon Eridani, and Vega, are produced by the dust from collisions between remnant planetesimals. Such disks are evidence that planetary systems have already formed. In comparison, the dense disks of gas and dust, such as those seen around the stars in Orion, are sites where planets could be forming right now. So now we're starting to observing extrasolar planets. A planet orbiting another star is called an extrasolar planet. Such a planet would be quite faint and difficult to see so close to the glare of its star. So I don't really like the term extrasolar planet. I shortened a little bit to an exoplanet. But there are ways to find these planets. To understand one important way, all you have to do is imagine walking a dog. You remember that Earth and the Moon orbit around their common center of mass, and the two stars in a binary system orbit around their center of mass. When a planet orbits a star, the star moves very slightly as it orbits the center of mass of the planet-star system. Think of someone walking a poorly trained dog on a leash. The dog runs around pulling on leash, and even if it were an invisible dog, you could plot its path by watching how its owner was jerked back and forth. Astronomers can detect a planet orbiting another star by watching how the star moves as the planet tugs on it. The first planet detected in this way was discovered in 1995, orbiting the Sun-like star 51 Pegasi. As the planet circles the star wobbles slightly, and that very small motion of the star is detectable by Doppler shifts in the star's spectrum. From the motion of the star and estimates of the star mass, astronomers deduce that a planet has at least half the mass of Jupiter and orbits only 0.05 AU from the star. Half the mass of Jupiter amounts to 160 Earth masses. So this is a large planet. Note also that it orbits very close to its star, much closer than Mercury orbits around our own Sun. So in image A, we will see a person walking a lively dog, a start off caused by the dog. So in image B, the star 51 Pegasi is pulled back and forth by the gravity of the planet that orbits it every 4.2 days. The wobble is detectable in precision observations of the star's Doppler shift. In image C, a person walking multiple dogs have a complicated motion. In image D, Doppler shifts of the star Epsilon Amadrea shown in the combined effects of the last 4 planets orbiting it. The influence of its shortest period planet has been removed in this graph to reveal more clearly the orbital influence of the other 3 planets. Are you all comfortable with this explanation? Yes, Mr. Visagi.
So can you hear me?
Yes, I can hear you.
Um, so if I'm understanding correctly, is it because the oscillation in the image A is happening in image B for one dog, and then for
Yes.
image C there's 3 dogs, so hence the oscillation gets a bit more complicated if I'm understanding
Yes, that's
correctly.
exactly what's happening. So if you look at image A and image B, if we have a star with only one planet around it, we would see a constant oscillation that's always the exact same size as the star and its planet orbits their common central point of mass. But in image C and D, it is where we have a star with multiple planets. So that means the Sun and each of those planets have a common central point of mass. And putting that all together, we will get a irregular oscillation that will repeat, and that will show us that there is a few stars in that system.
Thank you, sir.
Pleasure. So astronomers were not surprised by the announcement that a planet had been found orbiting a sun-like star. For years, astronomers had assumed that many stars had planets. Nevertheless, they carefully tested the data and made further observations that confirmed the discovery. In fact, of this writing, more than 3,000 extrasolar planets have been found by a variety of methods. So this textbook was written in 2017, and that was 3,000. I may be mistaken, but I think to date, 20,000 exoplanets has been found using this method, by making use of this method. There are currently 7 planets orbiting the star HD 11086 around Gliese 518 and 6 around Kepler 11. True planetary systems. Almost 600 such multiple planet systems have been found so far. Another way to search for planets is to look for changes in the brightness of the star when the orbiting planet crosses in front of the star, called a transit. The decrease in light during a planet's transit is very small, but it is detectable. And astronomers have used this technique to find many planets. From the amount of light lost, astronomers can tell that these planets with Jovian masses have Jovian diameters, and thus Jovian densities and compositions. The Spitzer Space Telescope has detected infrared radiation from 2 large hot planets already known from star wobble Doppler shifts. As these planets orbit their parent stars, the amount of infrared radiation from each system varies. When the planets pass behind their parent stars, the total infrared brightness of the system noticeably decreases. These measurements confirm the existence of the planets and indicate their temperature and size. Notice how the techniques used to detect these planets resemble techniques used to study binary stars. Most of the planets were discovered using the same observational methods used to study spectroscopic binary systems, but some were found by observing the systems as eclipsing binaries. In contrast, a few extrasolar exoplanets have been found by a technique called microlensing, in which an extrasolar planet passes precisely between Earth and a background star, briefly magnifying the distant star's brightness by gravitational lensing. Because lower mass planets or longer period planets are harder to detect, the planets discovered so far tend to be massive and have short orbital periods. Low mass planets don't tug on their stars very much, and present-day spectrographs can't detect the very small velocity changes that these gentle tugs produce. Planets with longer periods are harder to detect because astronomers have not been making high-precision observations for a long enough time. Jupiter takes 11 years to circle the Sun once, so it will take years for astronomers to see the longer period wobbles produced by planets lying further from their stars. You should not be surprised that the first planets discovered are massive and have short orbital periods. The new planets seem puzzling for several reasons. As you have learned from our solar system, the large planets formed further from the Sun, where the solar nebula was colder and ices could condense. How would big planets near their stars, called hot Jupiters, have formed? Theoretical calculations indicate that planets forming in an especially dense disk of matter could spiral inward as they sweep up gas and planetesimals. That means it is possible for few planets to become massive, short-period planets that are detected most easily. Another puzzle is that many of the newly discovered extrasolar planets have eccentric orbits, and a few others appear to have orbits inclined at large angles to the equators of their parent stars. Simple interpretation of solar nebula theory would predict that planets generally should have nearly circular orbits that lie approximately in their stars' equatorial planes, and do the planets in our solar system. Theorists point out, however, that planets in some young planetary systems can interact with each other, or with binary stellar companions, and be thrown into eccentric or highly inclined orbits. This effect is probably rare in planetary systems, but astronomers have found some of these extreme systems more easily because they have easily detected wobbles. You might be wondering if astronomers have been able to make images of any exoplanets. Getting an image of a planet orbiting another star is about as easy as photographing a bug crawling on a bulb of searchlight miles away. Planets are small and dim and get lost in the glare of stars they orbit. Nevertheless, astronomers managed to image a planet orbiting at the inner edge of the debris disk around the star Fomalhaut. Fomalhaut is, yes, Mr. Levuyo.
Is it possible, to like sort of what is the word? What is it? To sort of figure out how a planet looks like based on its chemical composition, like for example, the color
Yes.
of the planet.
Yes, that is exactly what we do. So we have techniques that we can get a spectrum back of the planet, and from the spectrum we can see its absorption and emission lines, and from there on gets as a rough chemical composition of what a planet is.
And so from these chemical compositions, so you can sort of tell like what color the gas in the the atmosphere of the planet is.
Yes, so from that we can roughly estimate what the chemical composition of the atmosphere is, and from there on we can make educated guesses if the planet could have life or not. And also that's one thing SETI is looking at, so the Search for Extraterrestrial Intelligence, is we know certain processes such as the Industrial Revolution releases certain chemicals in the atmosphere, and we call that tracer elements. So if we look at certain planets and we can see these tracer elements, that can also be an indication that there could be life on those planets.
Thank you, sir.
Pleasure. So, edge of the debris disk around a star Fomalhaut, using the Hubble Space Telescope's near-infrared camera, and around the star Beta Pictoris using a specially designed near-infrared camera plus adaptive optics on the Gemini telescope atop of Maruki. Both of those discoveries further confirm the predicted connection between the debris disk and finished planetary systems. So here in image A, we can see images of a Jovian-sized planet orbiting at 120 AU from the star Fomalhaut, at its inside edge of the star's previously known debris disk ring. The inset shows motion of the object between 2004 and 2012, at a correct rate of a planet at that position orbiting a star of that mass. And image B, image of a Jovian-sized planet orbiting 9 AU from the star Beta Pictoris. In both images, the central circular blank region represents a combination of hardware and software masks implemented to block light from the central stars that are much brighter than the planets. The Kepler Space Telescope, launched in solar orbit in 2009, searched for planets by the transit method mentioned in the previous section. Kepler's 32 visual wavelength charged couple device, so charged couple device is an acronym for CCD, monitored the brightness of 150,000 solar-type stars during its 4-year primary mission, detecting slight decreases in brightness caused by planets passing in front of some of those stars. Kepler's original search field between the constellation of Cygnus and Lyra was chosen to be close to, but not in the plane of the Milky Way, so that the number of solar-type stars was maximized relative to other type stars. As you know, the Sun's diameter is about 100 times larger than Earth's. Therefore, when an Earth-sized planet transits its parent star, meaning moves between you and a star, the planet covers up 1/10,000th of the surface of the star, causing a decrease of 1 part in 10,000 in the star's brightness. Remarkably, Kepler's detectors are sensitive and stable enough to detect transits that small, showing that is one hell of an engineering marvel. However, only a few percent of planetary systems can be expected to have orbits inclined parallel enough to our line of sight so the transit can be observed. That is the main reason why the target star sample was so large. So as we have looked in binary system, we can see when the planet moves in front of its host star, the brightness will dip a little bit. So transit light curve is what it's called. So transit light curve of the first confirmed extrasolar terrestrial planet, Kepler 10b. The planet has an orbital period of 0.84 days. The depth of the transit dip indicates that the planet has 1.4 times the diameter of Earth. Spectroscopic measurements with ground-based telescopes of the parent star radial velocity variations give a mass for the planet of 4.6 times Earth's mass. The planet's diameter and mass yield a density of 8.8 grams per cubic centimeter, higher than Earth's, indicating a mostly metallic composition. The Kepler search scheme involved very precise measurements, the brightness of each of the 150,000 target stars, at least once every 30 minutes, producing a tremendous amount of data that had to be carefully analyzed. The Kepler team was especially interested in finding Earth-like planets, meaning planets that are not only about the size of Earth, but also have Earth-like temperatures. Earth-like temperatures require an orbit of about 1 AU in radius of the parent star, has about the same mass and density as our Sun. You can see that an Earth-like planet around a Sun-like star will produce a transit only once per year. Each transit will last only 13 hours if the planet's orbit is exactly parallel to the line of sight, and even less time if the orbit is inclined. Thus, the Kepler investigators had an amazingly tough task of searching in the data for occasions when some of the 150,000 target stars, nobody knew ahead of time which ones, became a 0.01% dimmer than usual for a few hours once per year. And to be sure that the transits actually represented orbiting planets, at least 3 transits spaced equally in time had to be observed. Unless transits repeated on a schedule and observed variations in stars' brightness could have been caused by other phenomena. Thus, the Kepler investigators required at least 3 years of observations to discover and confirm each Earth-like planet. Of course, finding and confirming planets orbiting closer than 1 AU to their parent star with orbital periods shorter than 1 year is quicker. Also, you can see that will be easier because they will cover a larger fraction of the parent star during transit. Anyone to their question for the unmute mic? So causing a more noticeable dip in the light curvature. Just Kepler easily found many hot Jupiters within a few weeks of that start of the mission. After 4 years of observations and another year of data processing, the total number of confirmed extrasolar exoplanets discovered by the Kepler mission reached more than 2,000, with thousands more candidates waiting for confirmation. The majority of those planets are hot Jupiters or hot Neptunes, larger than Earth but smaller than Jupiter. About 150 of them are hot Earths. One star designated Kepler 11 has 6 planets, all somewhat larger than Earth, all orbiting closer to their parent star than Venus does to the Sun. Interestingly, because the Kepler 11 planets perturbed each other gravitationally, making successive transits come a tiny bit earlier or later than would happen if they were orbiting alone. Their masses can be estimated. The amount of light lost during these transits gives the diameter of the planets, and you know that combining the masses and diameters lets you calculate the densities. All 6 of the Kepler 11's known planets turned out to have densities like Earth or higher. Thus, they are definitely terrestrial planets. So here we can see an artist's conception of the Kepler-11 system. A few of the extrasolar planets and planet candidates identified by Kepler have transit light curves indicating that they are smaller than Earth in diameter. A handful of these systems have masses determined directly by radial velocity Doppler shifts measurements. So far, 8 extrasolar planets orbiting main sequence stars are known to be less massive than Earth. These are all hot Earths, in orbit so close to their parent stars that their surfaces are probably molten rock and metal. Note that several other objects known to have smaller masses than Earth have been found orbiting pulsars. In 2014, the Kepler team announced confirmation of discovery of the first known Earth-sized, Earth-temperature exoplanet, designated Kepler 186f. The planet orbits an M-dwarf star with 4 other planets previously discovered by Kepler. You can expect that space observatories will someday be able to image even terrestrial planets directly around Sun-like stars. The discovery of extrasolar planets gives astronomers added confidence in the solar nebula theory. The theory predicts that planets are common and astronomers are finding them orbiting many stars. And I'm going to end off this lecture tonight with a quote from Neil deGrasse Tyson. I'd bet almost anything that life from another planet is formed independently from life on Earth. Will be more different from all species of Earth life than any 2 species of Earth life are from each other. And that, ladies and gentlemen, is the end of this lecture. So now we've got an understanding of how planets are formed and that other stars have planets around them. So from tomorrow night's lecture, we're going to start looking at the planets of our own solar system. So tomorrow night, we're going to look at the terrestrial planets of our solar system. So before you guys log off, just a few admin related questions or issues. So firstly, as there are still students that have not submitted their assignment, I don't know if you have thought this through, but this is now ridiculous. So from tomorrow, I will deduct 50% of your assignment. And if you don't realize, this assignment counts 40% of your semester mark. So that is more or less the same as a semester test. So I would strongly suggest to submit an assignment, even if you get deducted, because that will help contribute towards your semester mark. If you submit nothing, you will get a 0 and your semester mark will be very, very poor. And in one other thing that's also a serious matter, I've started working through some of your assignments, and I have already found one student with 100% plagiarism. That is an extreme academic disciplinary hearing or disciplinary fault. So for that person that got 100% plagiarism, I have no choice that to submit your paper and plagiarism to the disciplinary committee of the university, and they will decide what your punishment will be. So worst punishment will be to be expelled from all universities internationally for a period of 2 years. So I'm going to give you guys I'm going to be a little bit lenient with you guys. If you have a plagiarism report of more than 30%, please contact me. I won't judge you. I will give you the opportunity to fix your plagiarism problem. If not, I will take disciplinary action against those students. So how is it possible to get 100% plagiarism? You copy directly from a website without changing anything. You don't even change the font. Yes, the similarity percentage is plagiarism. So 0% is good. Yes, Mr. Lavuyo.
So is it okay if I ask an unrelated question, sir?
You're more than welcome.
So, by chance, so do you know any people that work in industry, sir? And like, do you know whether they required like some sort of like further education to sort of get to their jobs?
Yes, I have a few friends that's in academia like myself, and I also have a few friends that's in industry. So it all depends what you want to do. So for generally in industry, when you have well, in computer science, if you want to be a programmer, it's generally preferred that you have a honors degree because to some international bodies require that you have a honors degree to be part of it. So usually for programming, you'll be fine with an honors degree. In industry, if you are a physicist in industry or do product development, then usually an honors is fine. But if you start dwelling into the research type of positions, some industries also have research positions such as the CSIR, then it is preferred that you have a master's. If you are in academia, then it's preferred that you have a PhD. But also putting it this way, industry and companies nowadays don't look at, so let me rephrase this. In the past, let's say 40 years ago, companies were only interested in what experience you had. Then in the 90s, early 2000s, there was a shift in they only looked at what your qualifications were. But now both of those models has changed and companies look at what can you contribute towards the company. And the candidate that can contribute the best towards the position is usually picked. But if you have two candidates applying for the same position and both can contribute the exact same thing, but the only difference in two candidates is one have an honors, one have a master's, then the person of the master's will be chosen above the person that has a honors. The same thing as well, if you have two candidates and both of them have the exact same qualifications and contribute the exact same thing, then they will look at who has the most experience. So there the candidate with the most experience will be picked. But it all depends on what you want to do. It all depends on where you want to end or what career path you want to choose.
And then so with this climate of like a lot of graduates not having being able to find a job, so like exactly, so what do you suggest one has to do?
So the problem currently in our country is we have a very, very high unemployment rate. So it doesn't matter if you are a graduate or didn't study at a tertiary education, the job industry currently is very difficult due to COVID and other economical circumstances. So the best way usually to make sure that you are recognized and people know about you is to put yourself out there. So that's why it is important to form connections and to build up your acquaintances and do networking. So usually before the days of COVID, there would be networking events at a university. So they will be hosting cocktail evenings or invite companies from industry to give a talk or provide lunch or something, and then students have the ability to network and socialize with people from industry. And there you will meet people, and when you graduate and you say, oh, I want to see if I can get a job at that company, then you already know who is the CEO of that company or the HR manager or one of the other managers, and you can contact them and say, hey, remember me from that networking event, and that helps a lot. So the best advice I can give you is to start networking as soon as possible.
And then, so do you think maybe by next year we will be able to get back on campus, or maybe like next semester?
Hopefully. So the plan was this year that we start bringing back students to campus in phases. But since we are now entering the third wave, that process has stopped. So the idea was for next semester that we would have about 60% of students back on campus. But unfortunately, that won't happen now. But the sooner everybody gets vaccinated, the sooner we can get people back on campus. For example, I look purely at statistics. So in the US, more than 62% of the population has now been vaccinated. And a lot of states and major cities are now relaxing COVID restrictions, such as New York. In New York, you don't have to wear a mask anymore because most of the population has been vaccinated and they are achieving herd immunity. One of my friends in Germany says most of the population has been vaccinated already, and they don't have any more new infections anymore. So as soon as our vaccination program ramps up, the sooner we can get back to campus.
Okay, thank you, sir.
Pleasure. Then I saw a question about the exam. So yes, because we are now on level 3 of COVID, the exam will be online. So guys, if you have no more questions, have a wonderful evening, and I will see you all tomorrow. I will remain active for another minute or two. Otherwise, have a great evening.